But what I want to do, we're kind of changing it from winter weather to one of the things I would like, what we really would like to see is the use of flash for flash flooding, and use that in concert with our other flash flood warning tools, including FFmpeg. So I want to just go over, there's some, I'm going to assign some of these courses beginning after the first of the year, but I want to go over all the things. And then I have a case from August we had at Myrtle Beach. So first, what I want to talk about is its flooded location and simulated hydrograph, or FLASH. Was done by NSSL, and FLASH relies heavily on input from our radar rainfall estimates. Limitations we'll see is the MRS QPE, which will directly affect the output we get, and poor low-level radar coverage will impact this. Hint, trees. QPE biases are not in there. Precipitation type selection is that a problem, and ZR rate caps cause the problem to get the maximum rainfall rates. Best practice is to compare your MRMS QPE to other sources to assess the biases when you have to make decisions on issuing flash flood products. Now, there's three models that the Flash uses. The three are CREST, SAC SMA, and hydrophobic. CREST is a couple routing and excess storage model. It's coupling any kind of upstream runoff to better simulate saturation in low-lying areas. The SAC SMA, or the Sacramento Moisture Accounting, it's been used for a long time. It's similar to CREST, except no percent impervious surfaces to model urban areas. So you have to remember that. And the hydrophobic, like the SAC SMA, except there's no infiltration in underlying soils. It is the worst case scenario, like everything's concrete. This would be especially for urban areas, burn scars, or when you get to impacts like Hurricane Florence, when you're just totally saturated 100%. And the products that come out of this that are important are the max stream flow, the max unit stream flow, and soil saturation. There's other ones, including the average recurrence interval and comparing the QPE to flash flood guidance. What is maximum stream flow? Here's an image to the right. It is the maximum surface water flow that has occurred over every point during a valid period. Its units in AWIPS are 35, cubic feet per second, are and that it's really in research, it's 1 meter cube per second, which is approximately 35 cubic feet per second. The resolution on all these products is 1 by 1 kilometer, and the temporal resolution is 10 minutes. The purpose of this, the stream flow, is to visualize the stream and river networks to identify broad areas of high flow. You should compare this with USGS gauging sites. It's best for identifying model biases. This product is not really used for flash flood forecasting. Now let's talk about the maximum unit stream flow. It's a normalized maximum stream flow by basin area at every grid cell. And the resolution is exactly the same as before. The units here are meters cubed per second per kilometer squared for research, or cubic feet per second per mile squared. And in AWIPS, we will see them in the imperial units. And one thing you have when you use this, 1 meter cube per second per kilometer squared is approximately 100 cubic feet per second per mile squared. And what you should note is when you see the values on these slides I'm going to show, they are in the metric units. So just multiply by 100 to get what the values are. And I'll show a table here to kind of give you a first guess. what is the applications for the maximum unit stream flow? Its primary use is to diagnose flash flooding. Max stream flow, as I said, is mainly for major river systems, while the unit stream flow is normalizing stream flow to a basin area, which highlights these significant flows. Research has found in general, and we'll have to make sure calibrate this for our area, is about 2 cubic meters per second per kilometer squared is a flash flow that's likely, reports will be likely. And if we get up to the 10 meter cubic per second per kilometer squared, significant flash flooding is likely. One thing, major point here, is if you have 1 pixel, let's say that's 20 cubic meters per second per kilometer squared, don't warn on it. You need a spatial continuity more than 1 pixel, a smaller area, maybe a block size, or 10 by 10 by 10 kilometers, something like that. And remember, until we calibrate the values for our area, which would be a great project for someone out there to use the maximum unit stream flow in concert with other flash flood tools. Now, the other thing is we can go back on the MRMS site that the flash data is available back for several years. Now, the next product I talked about was a soil saturation product. And all this is a model output water content in the top layer soils compared to the maximum storage. Its units is in percentage. Resolution still 1 kilometer by 1 kilometer every 10 minutes. Its application is to diagnose antecedent conditions conducive for flash flooding. What they have found, if you see values less than 50%, you will need additional rainfall to get some runoff. If it's greater than 50%, this area's already seen some significant rainfall, and you can do this in different time periods. And you can also compare this with what's in the flash flood guidance. So let's talk about what the limitations are. It's not the end all of all flash flood products. The MRMS QPE is fairly good, except where we have beam blockage. Right now, with the beam blockage to the southwest, most of Horry County is still okay. Anything right on the edge of the coast or out over the water, which we don't care about, is really blocked bad. But as time goes on, this is going to continually to get worse. It doesn't handle snow melt well, and Vicki tells me we're going to have to really pay attention to this year. It does not account for any releases from upstream dams. No forecast rainfall is used. The model flow is not calibrated in real time. Peak flows are still well represented, and there's no post-processing. Now, future improvements, you could probably see from what they want to do there. The QPE, they want to be able to incorporate dual pole, satellite, those type of sources. They want to incorporate rainfall estimates, actually use NWP models and extrapolate the rainfall being produced by the radars. They also want to improve some of the hydrological parameters that are used and use error models to correct force into model physics errors. Now, let's go and look at the strengths and some of the weaknesses here in each of the 3 models. On the left, we have the Crest. It's better in urban areas. It runs hotter than the SAC SMA model due to its quick ponding response. And it gives a first guess aerial coverage of flooding. The SAC SMA is the model that's used by the RFCs. It focuses on the small basin responses, and it saturates from the bottom up. And it resolves longer fuse high-end events. The other thing, it does not know impervious surfaces. So that's why Crest will perform better than the SAC SMA. Now, hydrophobic is used to determine the worst case scenario. You will always see it with a response and quick and early. Visual initial response and potential flood wave, you could use it for that. And here in their graphic, they're useful in burn scars. And like I said, during Florence, when you have the ground saturated or a hurricane, you could probably use it there. Now, how did they verify? J.J. Gorley et al. They and several forecasters from their work find that the crest was best. But you have to remember what the limitation and strengths of each one of those are. And you can see here they actually calculated over a 2-year period some of the statistics, probability detection, false alarm, and so forth. Now, here's the preliminary guide for unit stream flow thresholds. Less than 100. No, we're going to go with imperial units. Less than 100 cubic feet per second per mile squared. We'll just monitor it. You probably won't have any flash flood, but maybe some increasing flash flood potential. 100 to 200 CFS per mile squared. Monitor closely. You may want to start considering where, if I need to issue a warning, when it may be soon and for what area. Between 2 and 1,000 cubic feet per second per mile squared, there's a higher confidence in the warning issuance and impeding flash flood impacts. And over 1,000 is a likely significant flash flood. Please, these are just kind of a guideline, and that's something we need to, in the future, need to look on possible thresholds. Flash flood, there's also a product called Flash Flood Flash QPE to average recurrence intervals. Now, one thing you have to know about the average recurrence intervals, they're different than what we see in the Atlas 14. And the Atlas 14 is what's used in FFmpeg versus Flash. And the biggest reason that they used a different average rate or recurrence or intervals data is because some areas, especially Pacific Northwest, do not have that data available. So they wanted to make some kind of average recurrence intervals available for the whole CONUS. So how to use this in your flash flood decision? It's kind of difficult. There are many factors that aren't accounted: duration, the antecedent soil condition, and you have to remember there's a high bias may be seen in areas where totals exceed the 25 years or greater, because there's probably just not as many cases. Other products, we have Flash QPE to flash flood guidance. You see that's in the bottom right of our menu. Thanks for Jordan for sending that to me. One of the issues here is when we see these grids, they're on a national mosaic, not a mosaic, but a mosaic. Sorry, I've been to Chick-fil-A too much. Mosaic created there once an hour. So when this runs every 10 minutes, you're still looking at this national mosaic, which is still an hour old. It does not take into any changes to flash flood guidance, mainly made locally. Susceptible to low flash flood guidance after updates, especially when the ratios are greater than 500%. That is after a heavy rainfall event that fell in between when it was run. And why should you use to look at the ratios? You can look at these ratios without starting up FFmpeg. They're somewhat can be compared, even though they have different data that supports them. You can overlay this data with other products. Now, back on August 3rd, between 15 and 21 UTC, we had a flash flood watch out. It was excellent. I believe this is the one that Doug put a flash flood watch out, and plenty of excellent timing on that watch. Models shifted, didn't handle it correctly. But what we're going to do now is use the flash in real-time, short, near-term conditions. So what I have put here is on the right, you can see the LSR. We had a car stalled in 2 feet of water at 67th and Ballyhoo. There's a restaurant here, and here's a zoom. You can see there's a lot of retention ponds around this area. So that's what we're going to do. This is just north, I guess northeast of the big shopping area down there, Highway 501 and 17. But what we see on the left is 1516 to 18Z UTC, and that's the composite reflectivity. This is available through the flash guide, through the radar, but it's also available on the MRMS site, and that's where I've got all this data. we're going to look at what happened on this. We're going to mainly focus on the crest model. And what I've shown here is what the soil saturation, how it varied with time. You can see at 16Z, there had been a little bit of rain, but not too much. And then at 17, really about 1640, we started getting some heavy rain. And at 17Z, you can start seeing here that we're getting above, where the green is, we're getting above 50%, which is the duration when we should really start looking for impacts maybe to start happening. At 18Z, you can see a lot of it's just right along the coast. Very, very heavy rain in here. And the red is right on the edge of where it's actually the grid, but I would still consider it to be above 50, everything 50%. The quality of that, where the red is, I'm not really sure. Little confidence is not great there. And at 19Z, it's generally the same. So the event actually ended, the heavy stuff ended after 18Z, but still there was a runoff factor that we needed to take into account. Now that was the saturation. Now let's look at the unit stream flow for this time. And I just put 16, 17, and 18. Remember the values on the right here in the legend, multiply those by 10. Remember we had 100, we had 200 and 1,000, greater than 1,000 levels. You can see 16Z, kind of where the star is. It's kind of this area, what we're looking at more where this star is, and this circle where saturation. 16Z, we had no unit stream flow, but then you can start seeing about right here is where we're looking at, and it's between 200 and 300. So we not being familiar with it, always need to start watching it. Well, we look at 18Z, and I just took hourly snapshots of this, and you can see here we're starting getting areas above 400, up even we even have 600 to 100 meters cubed per second per kilometer squared there. So we've got an issue, and that spot for that restaurant is right here. So that's the crest unit stream flow. This is run, remember, every 10 minutes. I just did 1 hour snapshots. And then if you notice at 2030, here's the unit stream flow, and it's got less. And then you can see at 21 UTC, even though there is still some stream flow due to the runoff, most of the convection has shifted to the north, and it's a lot less into this area. Now, well, let's look at the average recurrence interval. You can see here I have it what it is for 1 hour, 3 hours, 6, and the maximum value. And you can see we're looking on the order of, and you say it can be high bias here, but it's more than a 25 year return. And you can see that go through. And then if you look at the overall max that we got out here, we're in the purple. So we're probably a 50-year rainfall. Like say it's high bias, I imagine there's some tropical storms that would move that down a little bit. Now, unit stream flow comparisons, I didn't show much of the other models. The top left, it shows where the location is with the star. That's the crest model. The top right is the SAC model. The bottom left is the hydrophobic worst case. And I wanted to show the actual stream flow, not the unit stream flow here, but the stream flow, and we'll talk about that in a second. But you can notice the crest, the orange here, it looks like we're between, and I did this at 1730, and this was like at the max heaviest rainfall rates. And you can see we're sitting there between 300 and 400, which is flash flood, and then you can see some values out. This is the LSR. So we got values here that are heavier, and that's probably falling into these retention ponds too, which means it's probably, if you look at these, they flow back down in here. So, and when they overflow, it's probably pretty flat. You can see in the crest, it's less, it's 200 to 300 because it doesn't have the impervious surfaces in it. And you can see the worst case scenario, we're shooting over 1,000 in that case, 1,000 cubic feet. Now, what I can show you here, you can also, it says you don't really use a crest stream flow for flash flood forecasting, but what it's showing is you can see what the flow is in the rivers. And one thing, when you start seeing it outside of the rivers, you know it's inundated and it's overflowing. So that's really kind of, that just gives you a guess. And if you look at some of this, the pictures when hurricanes are happening, this yellow, like in Houston, or even higher, was just over the whole county, not just in the bayous in that area. Now, last thing I want to show here is the precip rate, the QPE rate from MRMS, and I did these every 10 minutes, and you can see it's 1630. This is 1630, but it started about 0.6 hours at 0.6 inches per hour at 1640. At 17Z, it looks like it got about 6 inches per hour, and then it kind of fell back off. And the estimated, and this is not in a QPE rate, this is kind of a misnomer here, we probably got about 4 inches rain in less than 2 hours. So here you can tell, based using the CREST model and some of the base first guess fields, that yeah, we had a flash flooding event possible. This is over Myrtle Beach. Excuse me. When you get out over Columbus County, you may want to kind of use in between the SAC and the crest, because it's not urban and there's not as much impervious surfaces. So that's all I have. And what I want to tell you is, first of the year again, I'm gonna give, there's three short training sessions, and we a plan, and Vicky's going to help me. We're going to have a few case studies on this from some of the events in our area, just to give you a feel of how it works.